chapter 10, we're really going to start talking about the use of carbon material for the first time to do carbon-carbon bond forming reactions. We talked a little bit about this on Wednesday, where we had the difference in pKa's going from simple alkanes through alkenes to alkynes. And there is a vast difference. These are not just 25 units, this is a logarithmic scale. Okay, so this is the difference between a 25 Richter scale earthquake and a 50 Richter scale earthquake. There is a big difference. You've got to recognize now that these are powers of 10, so the acidity of this thing is just non-existent. This will not be taken off. But this now is workable. We can actually take those protons off with a strong base to be able to make something very useful called the acetylide anion. So a large part of chapter 10, leading into 11 and 12, is this type of process. You start to use a base that will do a job to take off a proton from acetylene. So if the pKa of acetylene is 25, you need a pretty powerful base, right? You need a carbon negative base, or you need a nitrogen negative base. And we'll see some examples here where it's used quite easily to produce this. And I left off on Wednesday saying that this guy is a really good nucleophile. This is small, compact, it's linear, there's no branching sticking out of it, so it serves as a very powerful nucleophile, and we'll do so in this chapter to be able to knit carbons together and start to do synthesis. The whole background to that, we argued, was based on hybridization patterns. We have sp3 versus sp2 versus sp. There's more s character involved in this orbital, which makes it a bit more electronegative, and therefore it's easier to hold on to those electrons, so it's a more stabilized system. And what we will do between now and the end of this chapter, the chapter is organized in a little bit of a different way. We come back to this at the end after we talked a little bit more about what alkynes do, and then we'll do this reaction. So you need a strong base, and you need to be on your toes as you start to plan to develop experiments, which is a big part of the second term. Can you use something like water here as the solvent? Why not? You cannot, but why not? Anybody? Why can't you use water or methanol or any protic solvents in that type of reaction? It's not a strong enough base. I'm not sure that's quite right. It's a very powerful base. But why can't I use water as the solvent? It's too reactive in what sense? It will. There was a section on this in the acid-base chapter. What was this called? Anybody remember this? If the solvent is more acidic than what you're trying to deprotonate, this was called something. No, it's been a while. Right, leveling effect. It was the leveling effect. Go back and look at that. You cannot use protic solvents here. So we'll have to use some of our polar A protic solvents to allow for this to happen. We'll talk about now appropriate bases, and some that are appropriate, some that are not. Anything with a conjugate acid which has a pK of less than 26 or 25 is not going to deprotonate an alkyne. You need something very powerful. So these guys at the top, extremely powerful, very, very powerful, very powerful. They are strong enough to deprotonate an alkyne to turn it into the nucleophile. The ones at the bottom don't work. What this will allow you to do, thinking about a comprehensive final, which is about 4 weeks on Monday, is to go back and look at this stuff again and to remember it and to make it sink in again. That review will help. So we can only use certain bases to do this, and maybe at the end of today, maybe Monday, we'll start doing that. How else do you make alkynes? There will be a very useful way of making alkynes where you knit two pieces together, but also if you have a system with the appropriate leaving groups, you can make an alkyne with the carbons already there. In this example at the top, we have, from the last couple of chapters, we talked about simple alkyl halides with bromine attached, and if you use a strong enough base, you can do this type of deal where you go after that proton, and you take this to here, you form a pi bond, and this breaks off. What was that mechanism? E2, exactly. That was a bimolecular substitute elimination process. Now, the difference in this chapter is we can also do this with dibromides. We'll make these things in a minute, but you can turn these dibromides into alkynes quite easily. And what it will involve, if you think about logic, strong base and alkyl halide gives an elimination. Well, how about two strong bases and two alkyl halides give two eliminations? So you can eliminate twice and make two pi bonds. And we'll do a bunch of that. Now, a lot of this is just review. If you think about alkenes and alkynes and how closely they are related, a lot of this will be reviewed from the earlier chapter. What we call a geminal dibromide here, in which we have two bromines on the same carbon, which we'll be able to make, we can take a strong base and we can do an E2 reaction. And that would give us something like this. But this now, unlike the alkenes that we saw earlier, this now has a second leaving group attached. So if you keep going with this, or if you start from the beginning and add an excess of that base, you'll go all the way to the alkyne. So the second elimination is very similar to what we've seen before. Base going after proton, pi bond forming, leaving group breaking off. Now, the fact that these are strong bases sets this reaction up. You think about the requirements here. These are typically oxygen bases or nitrogen bases, which are very powerful and therefore unstable. So it is the need of the base to become neutral and stable that drives the reaction. The carbon just gets involved to be able to transfer a negative charge from here to a bromine, where it's much, much better. Yes? Okay, moving along. What I want to get to is tautomerism, because that's great fun. This is something called a vicinal dibromide. We've made these in the previous chapters. We did this in chapter 9. You take an alkene and you add Br2, you get one of these things. So now we can use this. We can think about this as a strong base. And again, we'll just see the mechanism is fairly simple. One of these bases comes in, grabs one of the protons here, pushes 2 electrons up onto carbon, one of the leaving group breaks off, and then you do it again. And if you do this twice in sequence, you end up with an alkyne, and then that becomes very useful further on. So eliminations from the previous chapters, if you kept up with it, you've done the homework there, this is just the same stuff. So we have some ways of manipulating these systems to be able to give the functional groups that we want. But we have to be careful here. We have the opportunity now to control what happens. We're going to see a lot of instances, as we have, in which you can put HBr together in one instance or one direction, or you can turn the regiochemistry by changing the conditions. We're going to do the same thing here for alkynes, and all of a sudden this becomes like a big flow chart. You can go from an alkane to an alkene to an alkyne. You can go from an alkyne to an alkene to an alkane. You can go all over depending upon where you want to be. And the question might be, why on earth do all that? And the answer is, the planet gives us certain materials that we can start with, and then we have to manipulate those things to be able to make things we want. So starting at the top, if we take an alkene and we add hydrogen and a precious metal, we end up with an alkane. Is that an oxidation or reduction? Well, it says so at the top, doesn't it, Norris? Yes, it does. That's a reduction, okay? And that's the addition of 2 hydrogens. Hydrogen adding to something is a reduction. Now, this type of system, we've got to be careful here, and I do try to sort of emphasize this on a quiz or an exam. And obviously there's no quiz next week in class, but there will be an online quiz. If I just use one equivalent of this hydrogen, it isn't enough to be able to reduce that all the way down. So we have to introduce maybe a little thing that we haven't seen much of so far. Excess. Okay? Excess. More than one equivalent. At least 2 equivalents. And from lab, don't forget what I mean by equivalent, is if I have 1 mole of something and I want to add 1 equivalent, I need 1 mole of the other thing. All right? If I have 0.1 moles, I need 0.1 moles. If I have an excess, I've got 0.1 moles and maybe 5 moles. I have a huge amount. Often that's the solvent, but in this case, it's the gas. So what we'll find now is that this type of addition is kind of indiscriminate. It adds to the alkyne, and then it adds to the alkene that's formed. So that's very useful if that's the way you want to go. So keep an eye on this. This type of system starts out adding to the alkyne, gives you the alkene, and what's this telling you? What type of stereochemistry is that? Cis, so that was probably a syn addition, right? So was that stepwise or probably concerted? Probably concerted, right, because it gave the alkene. But you know from the past, so this is just an extrapolation of what you already know, that hydrogen and platinum will react with alkenes to be able to give you the alkane. Now that's counterintuitive in terms of what we have done, because crude oil gives us all kinds of these things, and we want to develop methods to go in these directions. But if you've isolated something from a natural product, from a plant, from a toad, whoever it was, and you want to go in this direction to make some pharmaceutical, you have to have these methods. The problem with H2PD is it's indiscriminate and it goes all the way. When you see this on a quiz or an exam online, make sure you recognize it's an excess of the gas. I'll always put that little excess in front to make sure we realize that. And it takes the alkyne all the way down to the alkane. You go through the alkene, but you can't stop at the alkene. So, very simple thing to think about. How about we try and affect that? How about we try and change that? It would be really useful in science if we can take the alkyne and stop at the alkene. And you cannot do that with those reagents, so chemists will come up with reagents to develop a method to do so. And this is something that you'll see on the exams, something called a Lindlar catalyst. I'll define it in a second. But the whole idea here is, can we do something controlled to stop at the alkene without going all the way to the alkyne? And yes, we can. These are the types of things that chemists will look at. The whole idea here is that you need hydrogen gas to be able to add, and you want to stop right here. You want to stop at the cis alkene. You do not want it to go any further than the alkene. So we will use something called a poison catalyst. This is a catalyst that has been doped with some extra reagents, some extra material, so that it just does not react with the alkene. It's okay to react with the alkyne, which is more reactive, and then for some reason it does not react with the alkene. So we have a selective process stopping at the alkene. Now, this is called Lindlar's catalyst. There's no mechanism involved here. There's really only one big mechanism left in this chapter. Everything else is pretty much additions and SN2s. Lindlar's catalyst is a mixture of quinoline, palladium, barium sulfate in a polar protein solvent like methanol. The mechanism for this is graduate school stuff. If you want to learn that, go to graduate school. But right now, it's a very useful method for stopping at the alkene. And the background to this is that the catalysis only happens in the first step. The alkyne is much more reactive. It binds to the metal. You do get reduction from the alkyne to the alkene, but it does not go any further. It does not catalyze the second step, so there's no rate acceleration in that second step from that catalyst. So the addition somehow, if this is fascinating, if you like this stuff, go to graduate school, for somehow this material and this material, as well as the precious metal, cancel out that second step. There's something about the way they bind together that slows that reaction down so much, or doesn't even affect the rate of reaction, that it doesn't go any further. So Lindlar's catalyst now is very useful. You can go from, let me put this in context, we can go from an alkyne to a cis alkene. Those of you who are making sheets of things and charts to be able to organize this stuff, this particular reagent system stops at the cis alkene. That's the key. Well, what if you want the trans alkene? What do? You develop something different. And if something different gives you a different outcome, then the mechanism must be different. Again, no mechanisms here. They're way beyond the scope of what we want to talk about. But we do have a very nice method for doing this. It's not a particularly fun reaction to work with. Alkynes themselves are not so dangerous, but sodium. I'm sure if you've ever seen people drop sodium into water, it's kind of fun, yeah? And potassium and stuff like that. And liquid ammonia. Now, liquid ammonia is loads of fun because it's a liquid. It's nasty stuff. So you have to mix these things very carefully. And the L right there means liquid. And if you do that, you get the opposite alkene, I should say. You start off with an alkyne, and you end up with this. And this is the trans outcome. Mechanistically, I'm not even going here just yet because it involves radicals. And we haven't covered the radical chapter. Maybe we'll talk about this in the second term. But it's a very useful complementary reaction to the one we just did with the use of the Lindlar catalyst to be able to stop at the alkene, and in this case, you get the trans outcome. So that's all you need to know is one and the other. Be careful, though. We're starting to do synthesis. We're starting to ask you questions based on, make this product. Here's a starter material. It might be 3 or 4 or 5 steps from the starter material to the product, and some of these reagents will be useful for doing that type of thing. So, if you start at an alkyne, and you want to go specifically to the cis alkene, you need to use this stuff. This stuff at the bottom doesn't work. Hydrogen and platinum on its own doesn't work because it goes too far. If you want to go from the alkene to the alkane, which you know about already from the previous chapter, you can use the H2 and the platinum. Down at the bottom, if you want to go all the way from the alkyne all the way to the alkane, just throw in some hydrogen gas and some precious metal and it'll work. But if you want to stop at the trans alkene, you now have this choice of using sodium ammonia. What we call a Birch reduction. Let me give you that term, the Birch reduction. Type of deal. And that now gives you some useful reactions. You have ways of going in and out of the very simple carbon-based material, changing the functional groups by simply adding hydrogen. Not much to that. So what we want to worry about next is what alkynes will do in the presence of other systems such as acids. A lot of this is logical. If you add acid to an alkyne, if you add acid to an alkene, what rule takes over? What's the governing rule behind that? If you put an acid into an alkene and the alkene is symmetrical, what are we looking for? Not looking for chiral centers. What are we looking for? There's a rule. There's a person's name associated with it. Markovnikov addition, to go through the beta carbocation to give the major product. It'll be the same thing here. You'll have a choice of carbocations on different carbons which have different substitution patterns, and you'll always go through the beta one. And then we'll talk about the complements. If we understood chapter 9 where we had H2O adding Markovnikov or anti-Markovnikov, we switch the reagents. You'll see the same reagents here doing the same jobs. So this chapter isn't too heavy until we get to the end of it. In this example, the alkene from earlier added HX, and we did this, and we went after that because it's a polar reagent, so it should be a polar mechanism going through a carbocation. In this case, a secondary is better than a primary, and we end up with the second step with the nucleophile trapping the carbocation, and you get your product. So that was earlier. Well, if we do the same sort of thing with one equivalent of HX adding to an alkyne, it should make sense that the X minus ends up in the same place, because you should get a better carbocation along the way. So this example, again, we'll think of something like this happening, and this breaks off, and we'd rather put the positive charge here, because it's kind of secondary-like. You can't really say it's secondary because it's not really an alkane system, but it's secondary-like. If you had an excess, where's it going to go? It's going to do the same thing. If I'm starting from here to go into the first product, this now can react with HX, and we can add that again, and we can go and do this, and we can put the positive charge here, and so the second nucleophile adds in the same place, and you end up with that. Now, why is that useful? That all of a sudden is very useful because just a couple of minutes ago we said these geminal dihalides are very good for making alkynes. So now we have a way of putting halogens in with 2 halogens on the same carbon, a dibromide on the same carbon. And the homework I've just put up for chapter 10 makes you think about this idea. Makes you apply the rules. Make sure you keep it together. Make sure you see it from chapter 9 and just apply the same rules. You should get the right outcomes. So we now have the possibility of, in a controlled way, putting one group on, X, and in this way, if we just add an excess, which you might see abbreviated this, okay, you get the dibromide, like so. Fairly straightforward in terms of the mechanism. Well, let's think about what we did earlier. If you had a non-symmetrical alkene and you added HX, you produced the better carbocation as the major process. Then the nucleophile came back in, and it gave us, in this case, the tertiary outcome. It should be very similar for this material, maybe with a little twist. So alkynes are reactive. Pi bonds are not held very tightly. They're easy to give away to electrophiles. In this case, well, you stop it over there. In this case, a proton, we're going to go after a proton, and we're going to form a carbocation. It's a little bit different. It's a vanillic carbocation. The plus charge is on an sp2 hybrid, an sp hybrid carbon, actually. So maybe it's not as stable as the guy above it, but still it's better than the other option. The other option is to put the plus charge here, which would be at the end of a chain, and you wouldn't have any help from any neighbors. So in this case, we get the vanillic secondary light carbocation, and that gets trapped, and that gives us this vinyl bromide. Same idea, same stuff. So 10 again is just a extrapolation of earlier stuff. Now, we need to be careful here. In this chapter, and I think in the addition reactions in general, we didn't say addition 1, addition 2. We spent all that time earlier saying SN1, SN2, and then we spent all that time saying E1 and E2. But in the chapters since, we haven't really talked about that. And the answer is because it's more complicated than it seems. If you measure some of these rates of reactions, you actually get a rate equation that is in third order. Okay? It's actually related to the HX twice. So these mechanisms are still a little bit gray. I'm fine if I think about what I want from you. I want this. This works. This is great. I like it. Okay? But there is evidence out there that you need two equivalents of the HX for this type of process, which means the mechanism maybe is a little bit gray. You could imagine now protonation happening and the formation of a positive charge right here. And if that vanillic carbocation isn't very good, well, let's maybe try to avoid it. If you think about how to avoid it, you can have a second molecule of HX here waiting to serve as a nucleophile. So the point of this slide is not to confuse things or to make things worse. It's just an indication of everything isn't as simple as we make out. You'll certainly see that in the second semester. Right? Things aren't quite as cut and dry or clear as they maybe are. So this slide is just a cautionary tale. Those of you who have to take biochem in the future, you'll see lots of rate equations. They're not always very simple, and you have to be on top of these things. But this is just an example of a more complicated system from organic. Now, if we want to switch the regiochemistry, then in the alkenes, we took HBr and we added to an alkene, and we got the Markovnikov outcome. If you wanted to switch the outcome, we put the peroxides in. In about 10 days, you'll know all about peroxides. You'll wish you'd never met them. We'll talk about those mechanisms soon. Everything will fall into place before the final. But let's think about this logically. If an alkene adds HBr with peroxides in that orientation, then surely an alkyne should too. And it does. Same idea, same type of material. You need to start off with the alkyne, you need to put some peroxides in with the HBr, and you get a switch in the regiochemistry. You get the lesser substituted product, whereas for the Markovnikov, you got the more substituted product. So now, think about this. We haven't talked about the mechanism yet, so let's put a big asterisk next to it and not worry about that so much. But in this case, because we get alkene products, we can get cis and trans. Okay? You'll see later on why, but you can get cis and trans. You can't get that in the reaction above because you have an alkane. And there's no possibility of cis or trans right there. So down at the bottom, just use the same reagent for the alkyne that you use for the alkene, and you get a similar type of outcome. All we're doing here is mopping up a few miscellaneous reactions that we can now start to use through synthesis. Questions, anybody? Engineers? Don't care, do we? Friday, it's payday, who cares? All right. Thinking again, extrapolating from what you already know. Take an alkene, non-symmetrical, add a proton in the presence of our acids such as sulfuric acid, phosphoric acid, something like that, which is non-nucleophilic necessarily, and we can get water involved. So is this polar or non-polar? Polar. Thinking about recitation, what we did to organize the material. Is that going to go through a polar mechanism or a stepwise mechanism? I'm sorry, a concerted mechanism or a stepwise mechanism? Stepwise, right? What's the first step? Pick up a proton. Pick up a proton and form a carbocation. So that's logical. That's what we have done so far. And we form a tertiary cation, then the water gets involved, we lose the proton, we end up with that product. Well, if that's the case for alkenes and you are comfortable with it, surely we should be able to do the same thing for alkynes, if they are indeed sort of the partners. Well, yes and no, right? We're getting into this part of chemistry that's really fun because sometimes yes and sometimes no, and sometimes both. So be ready. What we're going to do here is the beginning of a process called tautomerism. You've seen lots of different words this semester: regioselectivity, regioisomerism, stereoisomerism, stereoselectivity. We're now going to do something called tautomerism. I'll explain it in a second, I'll spell it out in a second. You have to practice this one. And the problem is, when you have an alkyne instead of an alkene, you have two pi bonds, and both of them are going to do something. The first one is going to react just like an alkene and give you this. Okay, see above, there was no double bond right here. That's just a single bond now. All of a sudden, we have this second double bond that was left over from the alkyne. And we get the first introduction to something you'll see an awful lot of in the next 17, 18, 19 weeks, whatever's left in the 2 semesters. That functional group now is not an alkene, and it's not an alcohol. It's somewhere in between. It's an enol. And it will have the properties of both. And the problem for you as you're learning this stuff, and you've got everything else to worry about for the end of term, is that enols quite often don't stay around very long because they have a more stable partner called a ketone, or in general a carbonyl. And we find this conversion at the end of these reactions, especially in acid like we have here, in which this enol, which yes is the formal product of addition of H2O across that alkyne, then changes into a ketone magically. Okay? This is now going to be something that you have to be concerned about. In a couple of slides, I'll show you the reaction that we did on the first day of class, and I asked you, are you ready for this stuff? Well, now we're here. And if you can handle what's about to happen, you can get through the class. If you can't, you'll be doing it again. So why is this important? Well, from now on, we're going to start talking about biological chemistry. We're going to start talking about the types of systems people have to worry about as chemical engineers on big scale. And we're going to realize that this stuff starts to get really important in applications. What we've done to this point is build up a bunch of rules, which we then just started to apply. We already applied we learned about the Markovnikov rule earlier, then we applied it to a new system, and it made sense that it should be the same idea. But many of you, even the engineers, have to take biochem, or should take biochem. And you have to worry about these processes in nature. For example, carbohydrates. If you look at the top here, we have this rather complex process in which this alcohol here seems to be turning into a ketone over there, and this aldehyde up here seems to be turning into an alcohol up there. Okay? And it's not just by magic. Most of this stuff isn't. We have something called an aldose turning into a ketose. You have simple systems here, such as D-glucose turning into D-mannose, going through D-fructose. We have a tautomerism process in which this OH seems to become a carbonyl, and then it changes again to become a hydroxyl. And it's all based on the same idea that alkynes do. So my contention is that we should start simple before building up to this. We should start simple with something like an alkyne, which is easy to follow, and then later on dive into this stuff at the end of the second term. And then for those who survive, can go on to do biochem. So these processes now are not just random, it's all leading somewhere. Well, here's your first sort of introduction to what we call tautomerism. I don't know if I've got that word on here just yet. Did you see it anywhere? Where do we see it? There it is, tautomerism. So that's a word that you should practice. Instead of singing in the shower, whatever you do, practice the word tautomerism. For those of you who shower. Tautomerism, say it out loud. Right, fine, good. Make sure you say it properly. This process is fundamental to all sorts of different things in biology, in genetics, in carbohydrate chemistry, in protein chemistry. This is a very, very important idea that you haven't seen before. Somehow, I need to turn this enol, which is the formal product of that first step, into this ketone. Why does it work? Well, it's an equilibrium system, and it turns out the ketone is more stable. You add up the bonds over here, the double bond oxygen here is about 170 kcals per mole, and this over here, the double bond down there is about 140. The fact is that the ketone is more stable. So we need to go there as the final product. So it's one of these sort of things that reveals itself after the first reaction is finished. The addition reaction is finished, and then you get the tautomerism. So let's think logically. We've got now acid, and we have a pi bond. In the earlier chapter, we added acid to pi bonds, and we got addition. We got a Markovnikov addition. So in this example, I've got a non-symmetrical alkene right here, carbon there and carbon there. If I had my proton, this picture here should make sense. The positive charge went to the more stable carbocation, the more stable, more highly substituted carbon. So that's a Markovnikov addition like anything else you've seen. What you haven't seen before is the availability of electrons that are not pi electrons or hyperconjugation type electrons. They are lone pairs. And this is the first example of what we call a heteroatom stabilized carbocation that you've seen. And this will be really, really key next term. A lot of the chemistry we'll be able to describe is based on this idea. If you have a pair of electrons next to a plus charge, that is a lone pair just sitting there not doing anything. Even something as electronegative as oxygen will share that pair. Because you look at what's the difference between these two. What's bad about this resonance structure on the left and what's better about the resonance structure on the right? Going all the way back to the beginning of term. Carbon has its octet in the right-hand picture. Now, the actual molecule looks somewhere in between because this is a resonance situation. But you're going to say that it looks more like this because carbon and all the other atoms have enough electrons to be happy. Well, that's not going to be a stable species because the oxygen wants its pair of electrons back. So the water comes in, takes off that proton, and we end up with a ketone. That process from left to right is tautomerism. And we're about to enter this sort of dangerous area where in certain instances you can catalyze with protons, and in other instances you can catalyze with bases. In this case, what's the pH? Is the pH greater than 7 or less than 7? Shouldn't have to think about this even if it is Friday. The pH is less than 7, right? It's acidic. So I'm not expecting any strong bases. I'm expecting protons. From our discussion in recitation, if the pH is less than 7, what are we looking at for intermediates? Positive or negative? Positive. And along that reaction profile, everything seems to be positive. And that works out. So be careful there. So what's happened under those reaction conditions from that previous slide where we had sulfuric acid, right? This is definitely an acidic environment. We are adding in the same way we did earlier, but then all of a sudden this is changing in the presence of acid through the tautomerism process, which is catalyzed by acid and later on by base, and we are turning into a ketone. So that is difficult. There's nothing easy about that at all. That's something that really demands your time. So here's the story, the end of the story. Take an alkyne. Typically unsymmetrical. In this case, it's biased so that you have a terminal alkyne in which one end is much better than the other. You form in the first step an addition product called an enol. There's the ene, there's the ol, enol, and then that goes undergoes tautomerism to give you ultimately a ketone. That is tricky, and that is where you've got to put the effort in to be able to see it. Now, flashbacks. This was on my first set of slides on the first day of class when we introduced who we were and what we did, where we were from, and what we expected from you. And realistically, of the 122 people I've got left in my class, maybe 90 will get through. So those 90 then, to go into the second term, and hopefully you'll be ready for this. If you can do this, you should be able to handle the second term. And from now on, you know the basics. You know the rules, you just have to apply them. If you haven't picked the rules up, this isn't going to work. We have a rather complex series of events. We have all kinds of arrows flying around. We have curly arrows. We have gray arrows. We have little arrows going backwards and forwards. We have these resonance arrows over here, and we have the big reaction arrow. That's everything in there that we've done so far. In the first step, protonate from the acid. Form yourself a carbocation. In this case, it doesn't matter because it's a symmetrical alkyne. Form a carbocation which then needs some help. Well, that help can come from the solvent because I have lots of it because it's in excess. And we can trap that carbocation, we can form this, which is the protonated enol. That protonated enol then can lose a proton back to the solvent, and that is the catalyzed addition of water to that alkyne. So I've consumed H3O plus up here. If it really is catalytic, I should get it back. I get it back in that step. That first process of that overall system is an acid-catalyzed formation of an alcohol, in this case an enol. But it doesn't stop there for most cases. In most cases, the ketone is more stable. So if we say there's chapter 9, here's the difference in chapter 10. It's adding two pieces together, adding two pieces in a modular sense to get a bigger mechanism. Well, I have an alkene. If you understood chapter 9, where we added things to alkenes, then this should make sense. An alkene goes after a proton, and we form a carbocation. Why put the carbocation there? You want it next to the O. The O has pairs of electrons to help out. That's the best situation. You then discuss resonance to see why that's better. This now is going to show you where the carbonyl is coming from. Take off that proton. If this is truly catalyzed, I should be able to use H3O plus in the first step, and I should get H3O plus back in the last step. And I do. And it certainly speeds things up. So now I've got myself a ketone, and we have a ketone synthesis. Anybody? It's going to be a great weekend, isn't it? Right. Of course, you're not going to see something as simple as that. You're going to be challenged with molecules that are more realistic and start to think about where they come from and think about these processes overall. These might seem at this point little, why is he doing this and why is he doing this, and it's all sort of broken up. It isn't. It is all going someplace. It's all going to chapter 12 to put all this stuff together. So my clues here: alkyne, reactive, 2 weak pi bonds, and I have acid, 5% aqueous sulfuric acid. Is that dilute or is that concentrated? That is dilute, right? So we have lots of water around. We expect the forward process to be favored. First step, what do you think? You have acid, you have an alkyne. What are we going to do? Protonate, right? So protonate. This is off the website, off those mechanism videos I've got out there. You should be looking at those by now, instead of wasting time on cell phones. Go ahead, pick this thing up, choose the regiochemistry based on the same criteria that you did in the previous chapter, in which you want the positive charge to go on the more highly substituted carbon. That's like a Markovnikov type process. Water then comes in as a nucleophile, traps that to give a protonated alcohol. In this case, there's the alkene, there's the OH forming. There's where you get your proton back in the last step, so it's catalyzed. And then in the next step, alkenes react with alcohols and water and acid. So we pick up the proton in this first step. We would say that this is the product of addition, whereas this is the final product that you actually isolate. Protonate from the pi bond, make the more stabilized carbocation here. Why is it more stabilized? Because oxygen can get involved in that system. You form this protonated, or it looks like a protonated carbonyl, take off the proton, and you have a ketone. So tautomerism, it's like IKEA. Everything's supposed to fit together, right? You go buy some furniture, and you figure out, put it together right. You never have any spare screws like I always do. You're going to put these mechanisms together. A lot of the second term is borrow a bit from here, put it together to explain something new. That's no more complicated than you make it. If you understand this stuff in the first term, that's kind of fun. So, stepwise, absolutely. pH less than 7, absolutely. Positive species all the way through, absolutely. If you understand that sort of idea, this should be okay. Examples. Looking at this, non-symmetrical alkyne. Adding H+, adding H2O. I have a system now in which both ends of my alkyne seem to be the same substitution pattern. So that's where I get 2 products from. This is not ozonolysis. I'm not breaking this thing apart. Ozonolysis comes in a minute. But I'm going to get 2 products because I can add to 2 different carbons. And since they're both secondary-like, you get similar stabilities in their stretches. Next one down. How many major products do you get from this one? Thinking in mind, if I put the OH group here, I end up with a ketone. And if I put the OH group here, I go through a lesser substituted cation. So how many products do you expect to be major? Just the one. That one. This means nothing to you. It needs to mean something by Monday. Down at the bottom, just a bit of extra, shrubbery stuff at the end, just to make you think, what's happening over there? And the answer is not very much. You've got protons, you've got water. How many major products do you expect? The one, because it's a terminal alkyne, and so you'll get much more of the internal, what we call a ketone, than you will of the other. So all there is to it. Okay? So we've been trying to build up organizational schemes here where I'm going to put acid and water in and I get the Markovnikov outcome. And then if my synthesis requires the opposite, where the OH group goes on the primary carbon, I've got to switch the chemistry completely. So what did we use to do that? We added acid and water and it gave you Markovnikov. What was the anti-Markovnikov? Say again? Not peroxides. Peroxides were used in the second step, but the first step to actually get you the correct regiochemistry, what was it? If you put the OH group on the tertiary carbon, it has to go through carbocations. If you want that OH group on the lesser crowded carbon, there's a clue in the words lesser crowded. What do I use? Boronation, the parachute, hydroboration. So this now is the complement to that. If you understood that in the previous chapter, this is just a little bit further. If I want to put the OH group at the end of the chain, I'm going to use hydroboration again. So again, I'm going to use the parachute. And I'm going to mention this because some of the homework uses this idea now. There's the parachute, okay? And in the book, it's abbreviated by its name, 9BBN. So for those of you who came to class today, there you go, freebie. You'll be able to do the homework now. 9BBN is the parachute. So what's the whole driving force of that? What was the whole point of the parachute? It was not driven by carbocations, it was driven by what? What is the cause of the outcome? Steric environments, the big pieces wanting to miss the big pieces. So if I add the parachute to this molecule here, just like we did for alkenes, I reckon the boron goes to the less crowded end and the hydrogen goes to the more crowded end. And that results in this case in the enol. In exactly the same way. Obviously after you do this, all the steps in there are the same. Don't learn this twice. All the steps in that process are the same as the steps as for the addition to an alkene. And that gives you an enol. But now there's a difference. The enol is at the end of a chain. And if I do the tautomerism here, I don't get a ketone because I don't have an extra carbon here. I get this. And what was that? Anybody? Aldehyde. You get an aldehyde. You maybe don't see this yet. Hopefully you will over the weekend. You are now building up a very useful collection of reactions to go wherever you want, at least within the bounds of what we've done. You want to make a ketone from an alkyne? Add H plus and H2O. You want to make an aldehyde from an alkyne? Add the boron and then do the workup. Those are the outcomes you get. And I'm saying this, I'm being straightforward here. This is second semester stuff. This is a measure of where we go the second term. If you don't like this stuff, then don't come back in January. If you're starting to get into this stuff and it's starting to challenge you, then great, you'll enjoy it. Well, there's a bit of an issue here. In this second step, what is the pH of this stuff, do you think? Is it basic or acidic? It's basic, isn't it? Now that changes something. That changes the environment. It changes what can happen in that tautomerism step. And again, this is foreshadowing the second term. If I'm trying to turn an enol into an aldehyde, in the presence of base, I can't use the same pathway that I used in acid. In the acid in the previous couple of slides, you can see here, dilute acid. Everything happened in an acidic environment. Down here, no. That second step is basic. So therefore, if the pH is greater than 7, what are the intermediates going to be, positive or negative? Negative. Is that sinking in yet? That sort of idea? Yeah? It's a good check to help you get along to the problem, solve the problem. So I have hydroxide. Hydroxide is basic and it's also nucleophilic. In this case, I have a proton. And that proton, have a guess at its pKa. What do we think the pKa is? And we're starting to ask questions that you should be able to answer. What is the pKa of a regular OH group on an alcohol? 16, right? 16. Turns out the pKa of this guy is lower. It's more acidic because that double bond is next door. And look at this. Once you take off that proton, you can delocalize. Every time you delocalized, that made the base weaker, made the acid stronger. So it should make sense now that this is it's not super acidic, but it's acidic enough for this to happen. And if I were to draw that, I could just dump the charge between the alpha carbon and the carbonyl carbon, and all of a sudden I see where my carbonyl comes from. That second resonance structure reveals the carbonyl. I go after the proton from the water. How have I got water in there? It's the solvent. There's lots of it. Go pick up that proton, you have an aldehyde. So you've now got the first introduction to acid and base catalysis to do tautomerism. Enormous in the second term. And it's hidden. It's kind of hidden. What do people do with this reaction? They tend to stop here because they miss the point. They tend to stop there. They tend not to go to over here. That's where we need to be. So maybe next Wednesday it's good that we're not here. We can think about doing some catch-up and we can start thinking about Chapter 11, heading towards the next exam, which is, I think, 2 weeks away. Sounds about right? A lot of stuff on that test. The third exam is the tricky one. I'm not done yet. Where are we going? I want to mention now that we have methods of going places, and then I'll stop at this slide. Catalog this stuff, categorize this stuff, organize this stuff. Do it today, do it tomorrow, or else you'll get lost. We have now developed methods to go in this direction from an alkyne and methods to go in this direction. On Monday, I'll finish this stuff off. I've got 16 slides left in this chapter. And then I'm into 11. And 11 is very different because it's radicals. So get consolidated on this stuff now so that when we get to 11, you're not lost.